Hello everyone. So in this video we are going to see about the Fourier transform and its properties. So this is the formula to find the Fourier transform of the given continuous time aperiodic signals. Actually, continuous time Fourier transform is applicable to continuous time aperiodic signals. For continuous time periodic signals, we can use Fourier series to convert the signal from time domain to frequency domain in order to analyze the continuous time signal, right? Whereas for continuous time aperiodic signal, we are going for the use of Fourier transform. So this is the formula. You can see this is the formula to find the Fourier transform of the given signal x of t. In frequency domain, the signal is represented using x of j omega, so which is given here, which is equal to integral is varying from minus infinity to plus infinity x of t e power minus j omega t dt. So this is for all omega values. So this is the value of the given signal x of t. And when you want to find the inverse Fourier transform of the signal x of j omega, in order to find the original continuous time aperiodic signal x of t, so the formula is given in equation 2. So x of t, which is equivalent to 1 by 2 pi, integral is varying from minus infinity to plus infinity, x of j omega e power plus j omega t into d omega. Here we need to integrate the signal x of j omega with respect to omega. Here also integral is varying from minus infinity to plus infinity. We are integrating the signal x of j omega with respect to omega. And you have to note down here in forward Fourier transform, here e power minus j omega t is present, whereas in the inverse or reverse inverse Fourier transform, here it is given as e power plus j omega t. So these two are the Fourier transform pairs, right? So for this, the first equation is called as forward Fourier transform, and the second equation is called as inverse Fourier transform. Let us solve problems related with Fourier transform. So first signal, which is given as impulse function x of t is equal to del of t. We know what is del of t, right? Del of t is simply an impulse function, which we can write it as del of t is equal to 1 for t is equal to 0. So only the function del of t is equivalent to 1 whenever the time value t is equal to 0. For all other values of t except t is equal to 0, del of t is equal to 0, right? So this is the function, impulse function. And now we can find the Fourier transform value for the given signal x of t. Actually, this is the um, formula to find the Fourier transform of the signal x of t. Here we can substitute, instead of x of t, we can substitute del of t, right? So it becomes x of j omega is equal to integral is varying from minus infinity to plus infinity del of t e power minus j omega t into dt. We know that del of t is equal to 1 for t is equal to 0. For all other remaining values of t, this function del of t becomes 0, right? So when you substitute the value for del of t in this equation, we will get this, right? So this is equivalent to x of j omega is equal to my integral minus infinity to plus infinity 1. 1 is nothing but del of t, right? So del of t is equivalent to 1. 1 into e power minus j omega t dt. So why we have this 1 means del of t have the value of 1 when t is equal to 0. So now, if we integrate it from minus infinity to plus infinity, only for t is equal to 0, we have 1. For all other remaining values of t for this integration is equivalent to 0, right? So we have here also when t is equal to 0, the value becomes 1. So if you substitute t equal to 0 here, e power 0, anything power 0 is equal to 1. So e power 0 is also equal to 1. So 1 into 1, we will get 1. So this integration value becomes 1. So what is the Fourier transform of the impulse function in continuous time domain? Del of t means it is equivalent to 1. Then let us solve one more problem with respect to Fourier transform. So given the signal x of t here is e power minus at multiplied by u of t. U of t also we know already. What is u of t? It is a unit step function, right? U of t is equal to 1 when t is varying from 0 to infinity. So we can write it as t greater or equal to 0. So it is equal to 0 when t less than or equal to 0. So this is the unit step function, right? So u of t is equal to 1 when t is greater or equal to 0, and u of t is equal to 0 when t less than or equal to 0. So this is the unit step function we know already. So here we can substitute the values for u of t in this equation. So this is the actual formula to find the Fourier transform of any given signal x of t. Here x of t is given as e power minus at into u of t. So we can substitute this e power minus at into u of t in the Fourier transform equation, right? So here we are substituting e power minus at into u of t for the function x of t here. Next, we can combine these two exponential terms, then followed by we can write the correct values for the integration here. Since u of t is available only from t greater or equal to 0, which means u of t has the value 1 when t is varying from 0 to infinity. Whereas from minus infinity to 0, u of t value becomes 0. So if you apply these values in the Fourier transform equation, here you can see, so integral is varying from 0 to infinity. In the previous equation, we have the integral value from minus infinity to plus infinity. But in this equation, we have the integral is varying from 0 to infinity due to unit step function u of t, since it is available. It has the value 1 from 0 to infinity. When we substitute the integral from minus infinity to 0, u of t becomes 0. So the entire function becomes 0 from minus infinity to 0. So that we are having the integral value from 0 to infinity here. Next, if we combine these two exponential terms, we will get e power minus of a plus j omega into t. So we know e power at multiplied with e power bt is equivalent to e power a plus b into t, right? And here we substituted, we have written the integral value from 0 to infinity, right? So here we are substituting u of t is equal to 1, right? So then we get integral is varying from 0 to infinity e power minus of a plus j omega into t dt. So which is equal to, when we integrate this exponential term, we will get e power minus of a plus j omega t. So the power term we are getting again divided by, so along with t we have the term minus of a plus j omega. So this is written in the denominator, which is nothing but when we integrate e power minus at into dt means, so this is the exponential term we need to integrate means, so then it is equivalent to e power minus at divided by minus a. So this is the general formula to integrate an exponential function, whatever it may be. It may be a complex exponential or it may be simply an exponential term. So this is the general formula. So instead of a, here we have a plus j omega, right? So if we integrate this, we will get e power minus of a plus j omega t divided by minus of a plus j omega, since we are integrating with respect to t. And here the limit is varying from 0 to infinity. When we substitute the upper limit and lower limit, we will get, so here minus 1 divided by a plus j omega, which means 1 divided by minus of a plus j omega is a constant term comparing to t, so that we are taking it outside. So minus 1 divided by a plus j omega into, when we substitute infinity upper limit, right? E power minus of infinity we have, e power minus infinity is equal to 0, minus lower limit we are substituting. Lower limit is 0. So e power 0 is 1. So we will get 0 minus e power 0, which is nothing but 0 minus 1, right? So here we have minus 1. In before we have minus 1 when we multiply. So minus 1 into minus 1, which is equivalent to plus 1. 1 divided by, in the denominator we have a plus j omega. So this is the Fourier transform of the given signal e power minus at into u of t. So we can write the Fourier transform of e power minus at into u of t is equivalent to 1 divided by a plus j omega. Thank you.